Okay. So far we've been looking at how to analyze beams using the geometry approach. All right. Um, so these are, if you look at it, most of the beams we've been analyzing so far have been statically determinate beams. All right. So we've been looking at statically determinate beams. Statically determinate beams, okay, whereby the number of unknown reactions is equal to the number of equilibrium equations. All right. So that typical example, if you have this is statically determinate because you have three unknowns, you have three equations, and the moment about a point is zero. So the unknowns are three, then the number of equations are also three. So E equals R. All right. Okay. You also know that if you have a case like this, all right, you have how many unknowns? One, two, three, so four unknowns. Your equations are three, but because of the this internal hinge over here, this internal hinge, your equation becomes three plus one. So in the end, you have four equations. So again, E equals R. Okay. We've come across these cases whereby you have, so there's a beam. The unknown reactions are one, two, three, and four. So four unknown reactions. The equations are only three. All right. So the unknown reactions are more than equations. All right. So that makes this particular beam statically indeterminate. What this simply means that the equations of equilibrium, the three equations of equilibrium, will not be adequate in solving this particular problem. So you need some extra or some more equations to come or to be able to analyze this particular what's the name? This particular structure. All right. So I'll briefly introduce us to continuous beams and what they are. So typically, the beam here is what you call a continuous beam. Okay. So then let's just look at continuous beams in, I mean, broadly, right? Okay. Okay. So we can define continuous beams are beams which are statically indeterminate. All right. So that's one definition to look at it. Statically indeterminate beams are typically continuous beams. Okay. Indeterminate beams are, so if your number of unknown reactions is more than the number of equations, then your beam is statically indeterminate. All right. So some examples are what we just look at one above. More examples could be this. All right. So these are statically indeterminate beams. There are four unknown reactions, and we only have three equilibrium equations. More examples. So this has four unknown reactions. This has three. Oh, sorry, this has three, and this has four unknown reactions. Okay. Then the case above also has four unknown reactions. We could have longer ones. We could have oops, this is too long. We could have so this has what, five unknown reactions and all that. So typically continuous beams are beams which are statically indeterminate. All right. So they are beams that you cannot solve them with information from year one of basic structures. All right. So let's define to define what continuous beams are. Okay. So these are also beams. So let's see. Beams which are supported by more than two supports. By more than two supports. Okay. So here, these two supports have to be roller and pins. Okay. No fixed support. There's also there's an asterisk to this. It can be more than one support. So this is more than two supports. Then you can also have a case of more than one support. So for more than one support, one of the supports must be a fixed support. Okay. For at least one. Okay. So this is also more or less like an asterisk. So even though I'm trying to define what a continuous beam is, I'm defining in terms of the supports. So if all the supports are rollers and pins, right, then it should be more than two. Okay. So if I draw this configuration here, the supports here are only two. So because the supports are here are only two, and also they are rollers and pins, it means that this beam here is not a continuous beam. So not continuous. All right. But then what? But in the case where I introduce one extra, so the same thing, I introduce one extra support. So now the supports are three. So this has three supports. So this then becomes a continuous beam. Okay. This has only two supports. Now for the hysterex component, if I have this, so this a cantilever, right? So only one fixed support. So one fixed support only. So hence, oops, sometimes things don't move the way you want them to. So again, this is not continuous. All right. But what if I take this beam? All right. And then I add another support. Okay. Then this becomes a continuous beam because it is simply one fixed support plus additional supports. Okay. So this additional support can be any support. It can be a ruler, it could be a pin, it could be a fixed support. So this is continuous. All right. So we could have different types of deflected shapes. Okay. So typically, if you have, let's say you have a beam, okay, that has a pin support, and then some rollers, on it, and then you have some distributed load, okay, on it. Let's call that load AUDL so that it makes sense to us. Okay. So if this is the loading, I can redraw the same beam. Sorry, this end is pinned, okay? If one end is not pinned and all three of them are rollers, they become, even though it is statically determinate, they become unstable because they have no reaction to any horizontal loads. And once there's a horizontal load, then the system begins to fail. All right. So that's how come we don't have a beam with rollers at all ends, because then that becomes an unstable structure. All right. So this then becomes our deflector shape. So it deflects this way. So this is how the beam is going to bend when you apply this particular load onto it. Okay. The supports will not move, but then the spans will begin to deflect downwards. Okay. Here we are assuming the load is downwards. If the load is upwards, then the deflector shape would also be upwards. Okay. So this is the deflector shape or curve, or the deflection curve or whatever. Okay. Deflector shape, I think, sounds better. Okay. So this works for what's the name? This works for a continuous beam. Let me draw another bit of it. Okay. Then the bending moment diagram of this particular beam would look like this. Okay. So this is the bending moment diagram. It looks different from what you guys are used to. Sometimes these things become a little bit confusing, but it's fine. I prefer to draw my bending moment diagram this way most of the time, and the reason is because usually it follows the general uh, behavior in terms of the deflection, but what we are used to. So this is correct, but I just draw another one. Um, Copy paste. What we are used to is this. Let me choose this color. So we are used to something like this. Okay. So that this is positive, 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 and this is negative, negative. Okay, so here this is my positive, 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 negative, negative. Okay, it's the same thing. All right, it doesn't matter. I think I'll try and stick with the one below. All right, so that we have some sense of convention. All right, so they both are bending moment diagrams. Okay, just that to go with the typical X and Y axis, this is what we do. All right. So it's fine. We don't need to stress ourselves about it. They all are the same. Okay. So typically, this is what you would experience if you have any beam with this type of loading. Okay. So if there's a uniformly distributed load on the beam, you have the corresponding deflected shape, then you also have the corresponding bending moment diagram. Okay. There are other more deflected shapes. We okay. So before we move on, the negative side side um negative side of the bending moment is it's called, or is a hogging moment. All right. And then these this is over the supports. Okay. And then let me, okay. This looks nicer. So, which implies that the positive side, I can also write something very similar. So the positive side of the is called the sagging moment, and it occurs this occurs in the spans. Okay, it's not always the case, but then for now we can assume that is it. Okay, it's not always the case, but then we can assume that it is for now. All right, so it means that the shapes in here, these shapes, okay, are the sagging moments because they are occurring at span. See, when you draw it like this, it makes much more sense because then you actually see the sagging, like the bending downwards. Sagging means bending downwards, right? Whilst the hogging means bending upwards. So if you draw it with my idea, it gives you that visual experience of the sagging and the hogging. All right, it doesn't make anything wrong, anyways. Okay. Then the hogging is what happens over the supports. So that's something to take note of. Okay. We can also have some different options. Let's say I have a beam. So here, instead of a pin support or roller support at the ends, now I have two fixed supports. The same idea. Your deflected shape will be slightly different. So I'm going to, so let's say there's a loading on it, a UDL. Okay. Let me just copy these things so that I don't have to draw them every time I'm doing these. Okay, great. Okay, so I think you can go away. Great. So the deflected shape, I think I drew with the green. It starts, so it starts as a straight line, then it bends, then it bends, then it comes down. Okay. So this is how the deflected shape looks like. Okay. The key difference has to do with the ends, the support ends, right? Because when the supports are fixed, there's no rotation. Okay. Then the bending moment diagram, I'll draw my version. I'll draw the one we are used to. So it starts like this. Okay. So you can see that for that one, the ends of the bending moment do not go to zero, but they actually have a value. Okay, so just take note of it. So this is the same as oops. This is the same as something like this. So they are both the same. All right. So now this is negative, negative. This is positive, positive, positive. Then here I have positive, negative, 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 positive, positive. All right. So that's the idea. All right. And so we could have different configurations of this. Okay. Uh, okay. So as I mentioned, that these are generally the case. In some cases not exactly that, but generally we could assume that this is what happens. Now the question is, how then do you solve these types of beams? All right, because they are continuous beams. We don't have enough equations to be able to analyze them using the three equilibrium equations: summation of moments about a point, summation of forces in the x direction equals zero, and also summation of forces in the y direction equals zero. Okay. So we need to figure out how to solve these types of questions. All right. And there's one topic like that, which we called the three moment approach. So the three moment equation method. Right. So this is a method used to analyze continuous beams. Okay. So so let me just indicate method. It's called a force method. We'll look at so the force method. Let me just put here force method. We'll look at what these things are. Force method used to analyze continuous beams. Okay. So to help us to draw our shear force and bending moment diagrams, right? the it was I think was proposed or presented by what's his name again? Clapeyron. Yeah, I think Clapeyron. Clapeyron presented this method in 1857. All right, so that's 100 years before Ghana gained independence. All right, so that's the difference between the time difference between when this method was proposed and then we gained. So it's been in use until again recently that due to the advent of computer and its computing power. So there's been a shift from force methods or what we call mostly flexibility analysis to more of the displacement mode, which is the stiffness method analysis. We'll look at this later, what all of these things mean to us. All right. So it was brought about by Clapeyron in 1857. So it's used for the analysis of continuous beams, and it is a convenient tool. It's an easy to use tool, right? So it's convenient. We'll look at. Hopefully, I can spell my convenience right. It doesn't look like that's correct. Convenience. All right, whichever one works. Okay. So it's a convenient tool for continuous beams analysis. Okay, it's like I'm writing the same thing again. Okay. And for us to be able to use this method, we are working within the elastic region, not plastic. Okay. Once it goes to plastic, everything changes. Okay. So we are still within the elastic region, and that's where most designs are done. Most structural designs are done within the elastic region. Okay. So one other thing is that this method, before we formulate equations for this method, we have to make some assumptions so that it's easier for us to work with it. We whose birthday it is? Okay, sorry. I got a bit sidetracked. Okay. We assume that the slope of the elastic curve, the curves we've been drawing. So this is the loading, is elastic curve or the deflected shape. All right. Okay. So the slope of the elastic curve is continuous over the interior support. So any support in here, so the support at the end, these are called exterior support. Okay. And then if they are inside the beam, then they are called interior support. I think we've gone through this earlier. So just that's a refreshing of our memory. Okay. So we also assume that this assumes that the slope of the elastic curve is continuous at an interior support. Okay, so let me just explain that very quickly. So let's say if I have a beam, okay, and this is my interior support. We are saying that the slope, when you take, okay, so if this is the elastic curve, if you draw a tangent at, let's say, let me call this B. If you draw a tangent at B, okay, so there are two tangents at B. This here, let's say theta B on the right-hand side, and then theta B on the left-hand side. Okay, for us to be able to use this equation properly, we are assuming that theta B on the left is the same as theta B on the right. That is not always the case, okay? But then for simplification, if you do like a proper three-dimensional analysis or experiment of a beam in terms of how they behave when loads are applied to them, there's a slight difference in the rotations at the point B, right? But then for the purposes of simplification, we can assume that these differences are very minute and they might not affect the overall behavior of the structure. All right. We in engineering, we deal a lot with assumptions, all right, because otherwise analyzing structures in their general form will be time consuming and then overly cumbersome. And again, that will not really reflect much on the overall behavior of the structure. So we make some assumptions, all right. And one of those assumptions is that the slope on the left side is the same as the slope on the right side for any interior support. Okay, and that's to indicate that the elastic curve is continuous. Okay. um, this equation method. So the equation that we'll be using. Okay, involves three moments. Okay, three moments, and these three moments our focus usually is on the bending moment as the support. We'll look at these things here next week, yeah. And the supports under consideration. And then we also look at so the three moments. One of those moments is the bending moment at the support under consideration. Then the other moment would be the bending moment at the two adjacent supports. Okay, so I'll explain this and we can bring the class to a close. Okay, so what this means is that if I have a continuous beam, right, with a series of supports in there, okay, this is A, B, and C, and D. All right. So assuming what happens is that we when we are trying to solve for, let me add the last one, E. When we're trying to solve for these types of problems, we make the moments redundant, and then we formulate equations, and then later find these unknown redundancy. We'll look at that next week, okay? But just to explain to us what the three moments are all about. So for example, if I want to find, or if I'm considering, let's say B, the moment at B is under consideration. Okay. If like that is the key thing I'm looking at in terms of the calculations of finding the moment, or where I'm formulating the bending moment equation or the three moment equation in this case, and B is my target, then it means that B is under consideration. So B becomes the bending moment under consideration. And then I need to add two adjacent moments at the supports. All right. And those to the two adjacent supports would be at A and C. So here I'll be focusing on something like that. Okay. With B being the main one under consideration. Okay. So the adjacent are the moments on the left and on the right of the moments you are considering. Okay. So in that vein, if I'm considering, and let's say the moment at C is under consideration, it implies that then the moment for the two adjacent support will be B and D. So again here, this is more or less what I'm looking at. Okay, so then here I'll be focusing on C, and then we keep on going and going. So for any particular problem, you might have a series of three moment equations because you have to be considering every support. So every support would have to be under consideration. So we'll end up with a series of bending moment equations, all right? And then we'll solve for them. So there'll be sometimes there'll be a bit of simultaneous equations, either three unknowns or two unknowns or whatever, and we should be able to figure that one out, all right? So this just to introduce us to the three moment equation method. When we meet again, we'll go through it a bit more, formulate the equations, and then solve some problems with respect to these equations. All right. I think that's about it. If there are any questions, please, you can ask.
Then I was wondering if we could get an extension on the submission for the assignment. I'm trying to log into every campus. It's not working.
Yeah, but then the submission was yesterday. It wasn't, it's not today, if I remember. Right. The deadline was because the deadline is always a day before the class. And we've had what 2 weeks to get this work done. That's more than enough time, everybody, please. Okay. No assignment is 1 week. I think all assignments have been given to you guys. It's okay. So welcome to CENG 255. Theory of structures. All right. The last time we had this lecture, we were introduced to I think we completed the conjugate beam method, one of the geometry methods. The geometry method used to analyze structures by calculating deflections and then slopes, right, or rotations. And then from there, I think we introduced to continuous beams, right? So we tried to understand what continuous beams were. We went through understanding that, like, comparing what we meant by statically indeterminate beams. Typically, that's a external indeterminacy. So we're looking at the statically indeterminate beams and then explain what continuous beams are. So we took a typical continuous beam. All right. So we have this continuous beam right here in this space, okay, which has 4 supports. All right. So there's the excuse me. Let me do this before I forget. Yeah. Sometimes these things. All right, so good. Yeah. So we have this beam which has 4 supports, right? 2 at the ends and then 2 interior. Okay. So if we have some kind of loading, let's say in this case we have a uniformly distributed load. On the what's the name? On the beam, the deflector shape of the elastic curve will take this form. So it goes this way, that way, and this way. All right. And then I also explain that because if the reason why we have this shape is if you assume that there are no support settlements. All right, so no support settlement. Okay. Or no support movement. I mean that if the supports are rigid in place, then this becomes a deflected shape. Okay. All right. And then based off the deflected shape or based on the loading, we can draw our bending moment diagram. And then I mentioned that in drawing the bending moment diagram, there are 2 school of thoughts on how to draw the bending moment diagram. Okay. What we are used to is that the positive phase of our bending is upwards, and then the negative component are downwards. So typically we use this approach right here. Okay. So we have positive upwards and then negative downwards to conform with a typical X and Y axis, okay? Where for any X and Y axis, looking at the Y, it's positive upwards and then negative downwards, okay? Then there are also some school of thought whereby we can draw our bending moments in this form. All right, they both are the same, whether positive is downward or upwards, they both are the same. The second option, or this option here, let me call it, let's say option A. Option A is preferred in most cases because it also follows the general um, behavior or the general pattern when it comes to the deflected shape. Okay, so some people just prefer that because then it's like also when looking at the deflected shape, there's conformity with that. But then because we have been working with option 2 or option B throughout this course and then first year basic structures, we are most likely going to go with the option B. All right, so that we just work with conformity. All right. And I explained that typically when looking at continuous beams, they tend to have, so you can see from here that when the ends, so the supports at the ends, right? Oops, let me just use a different color. Okay, so the supports at the ends, this is even worse. Do I have a nicer color here? Okay, let me try the green. So the supports at the ends here are simply supports, or they are pin supports, or they are pin supports. And we know that pin supports do not have resistance against moment. All right, so the reactions for moment at pin support or pin support at the ends of a beam are zero. Okay, so that's how come when drawing a bending moment, we can say that assuming I have here to be one, these things, so here's 1, 2, 3, 4. So I'm naming my support 1, 2, 3, 4. All right, so it means that the moment at support 1 will be 0, and the moment at support 4 would also be 0. All right, but because support 2 and then support 3 are interior support, so I think we already mentioned that these, so the 2 here are interior supports, and then the 2 at the ends are called exterior support or end support. So some will say exterior and some also say end supports. Okay. All right. So if for interior support, the moments at those interior supports are not 0. All right. And that's how come when we drew the bending moment diagram, there is this value right here at these ends. We don't know what they are, but typically they are not equal to 0. Some cases they might be depending on the loading, but normally they are not equal to 0, or usually. So let me say usually M2 and M3 are not, it will not be equal to 0. Whilst sorry, what kind of mistake is this? M1 and M4 are 0. So this one always 0. Okay. All right. Then we can also have the case whereby the supports at the ends. So again, support 1, 2, 2, 3, and 4. The support at the ends might not be pin support, but they could be fixed supports. All right. So if the supports at the ends are fixed supports, then there's a likelihood that all the moments at all the supports, regardless of where they are positioned, will not be equal to 0. Okay. Normally it's wrong to write it this way. So M2 will not be equal to 0 because they could have different values. So you cannot equate them to be the same. All right. Oops. Will not be equal to 0. And the M4 will not be equal to 0. Okay. So we can see from here that the elastic curve for a continuous beam that has fixed support at the ends are slightly different in the sense that the curve, because at fixed support there are no rotations, right? So the elastic curve comes and goes as a straight line almost towards the fixed support, so that theta, let's say at 4 here, will be 0, and also theta at 1 here will be 0, but here theta at 2 will not be 0, and then theta at B will not be 0, or theta on the left side of so maybe 2, let's say theta at 2 on left side will not be 0, and theta at 2 on the right side will not be 0, and the same here too. Theta at 3 on left side, so this is the left side, theta, so theta 3 left, and this is theta 3 right. Okay, so theta 3 right will not be equal to 0. Okay, so maybe then here's theta 2 right, and here's theta 2 left. Okay, if I'm to draw a tangent at this point. Okay, all right. So typically, this is our bending moment diagram for a continuous beam that has these support conditions. Okay, you can either use either this option or that one, but I think we'll just go with this because that's what we are used to. All right, but some books would prefer the left side. So in case you come across some textbooks that uses the left side, it is not strange. All right. Okay. So we were also introduced to one of the force methods to analyze continuous beams or statically indeterminate beams, and one of these force methods was to look at what we call the three moment equation method. Okay, and it derives its name from the fact that if you have a continuous beam and you want to determine what the reactions are, which you can use to draw your bending moment diagram, one of the things you need to look at is to first be able to calculate the moments at the supports. All right. And for any beam, when calculating the moment at the support, we look at 3 supports. Okay. So we usually look at 3 support at a time. Okay. So look at 3 supports at a time. Okay. Or at every instance. All right. So that's where the 3 moments or the name 3 is coming from, because we end up trying to find a moment of 3 supports at every time. And then in finding the support, we have should I say a center support, and then we have 2 support adjoining it, one on the left and one on the right. Okay, so in this case, if we want to consider support B or determine the moment at support B, then we need to have 2 adjacent supports, one to the left of B and one to the right of B. Okay, so in this case, that would be so if we are considering support at B, that means that we need to look at A and C on the left and right of B, respectively. Then we can also consider support C, or the moment at C, all right? And if we are to do that, then it means that the other supports on the left or right of C would be B and D. Okay. Then we can also consider, we can do moment at, let's say, D. Okay. if moment at D is under consideration, then it means that our two adjacent, or some will say adjacent, supports would be at C and E. Okay, so that is the idea for um the three moments equation method. Okay, one other way to look at it, do I have space to type in this? Okay, one other way to look at it is that in the first case, in this case here, we are considering span. We are looking at, let me write that in black. Spans AB and then AC. And sorry, BC, not AC, and BC. Okay. Then for case two, or where we are looking at C as our what's the name? Our moment, it means that we are looking at spans BC and then CD. Okay. Then for the third one, we're looking at spans CD and then DE. All right. So that's also another way to look at it. Okay. So if you look at span AB or segment AB and then segment BC, the common point between the two spans will be B. So in that case, B becomes our point under consideration. Okay. That's the reason why I'm going through over this, because at some point we'll need that understanding to derive equations for the moment, the three moment equation method. Okay. All right. Was there something else I added? Yeah. So this here, which is very important. Typically, when you have a beam, okay. So let's say, so let me bring this down here. Let me just copy it and bring it down here. Okay. All right. When you have a beam, okay, and then so let's say this was derived from let me just put something here. Okay. I mean, this beam continues all the way, so what I have interest in is B. Okay. So it means that this is my elastic curve. Okay. It looks a bit funny, but oops. Okay, so actually I drew a continuous. Okay, so something like this. Okay. So our focus is on B. Now, if I draw a tangent, okay, so I have these two tangents drawn from B. So let's call them tangent B for both cases because they are drawn from B, right? So tangents drawn from B, I mean, with respect to the slope, it looks a bit strange because my curves are not really that good, but let's just go with it. Okay, because normally the curves will not go beyond the tangent. Okay, now we have a slope here, theta B left. So another slope here, theta B right. Typically, when you sum these two slopes, theta BL plus theta BR, they give you a certain theta. Okay, it's not equal to zero. Okay. So this is not equal to zero. Okay, because normally there is what we call discontinuity at supports. Okay, loads cause discontinuity at supports, which means that the slope on the left side of the beam let's say of the support B, which is theta BL, and then the slope on the right side, theta BR, will not be the same. There'll be some discontinuity. Okay. But then that makes it difficult for us to do any meaningful calculations. Okay. In reality, the two slopes are not the same because of these continuities, right? But then that makes, again, as I said earlier, makes it difficult for us to do any meaningful calculations. Okay, so we, as part of our analysis, we assume that the slopes of the elastic curve is continuous at any interior support. What it simply means that um, the curve, so this elastic curve here, it doesn't break, it continues all the way. Not normally, or in reality, the elastic curve at that support might look something like this, and maybe there'll be a different one, maybe. So each one will have its own. So if you draw a tangent at these points, you realize that the theta here, let's say theta 1 and theta 2, theta 1 plus theta 2 would not be equal to 0 because the slopes are different on both ends. Okay. But the guy said that means for difficult calculation. So we are assuming that there's no discontinuity. The slope is continuous across the supports, which means that in that case, the theta b on the left plus theta b on the right will be equal to 0. Okay, so if you sum the two of them up, they should be equal to 0. Okay, because if this is moving counterclockwise and this is moving clockwise, when you sum the two of them up, it should give you 0. So that's what we mean. So this is what the continuity of the elastic curve, continuity of the elastic curve does to our equation. Okay. All right. So again, as we usually make some assumptions because in engineering, it is almost impossible to get the exact, precise value for any calculations. You could get very close to the exact value, but then we are not interested in the exact value because there's always probability in engineering, especially structural engineering. So if there's probability, and this probability of can come from, let's say, for example, if you are building a house, the carpenter that does the formwork, if the wood that is used for the formwork is not straight, there'll be variations in your beam sizes. Even in placing the rebars in the formwork, there can be variations. Even the rebars that are sold on the market have different sizes along the length of the rebar. So they don't have exact values out there. So there's no need to come up with solutions that will give you the exact value. It's because exact values calculations are cumbersome and time consuming. All right. And we don't need that degree of accuracy. Okay. So we make assumptions to get values which are acceptable within a certain probability range, whereby failure of your structure will likely not occur. Okay. So engineering deals with a lot of probability here and there. Okay. All right. So let's see how to derive the three moments equation. Okay. That's why we are here. So let's see derivation of uh, the three moments moment equation or method equation or whatever. Okay. So let's see. Let's take a beam with some arbitrary loading. So let me, times it's just nice to draw things nicely. Okay, this looks nice. So I have a beam at one end. I need how many supports? 5 in all. Okay, so I think I got my 5 supports. Great. And let's say I have some loading on it. Okay, some distributed load. It's not a UDL. It's just an arbitrary distributed load. Okay. So we have the loads. Let me just delete some of you. I don't want to write all this plenty. Okay. So we go down here. Okay. Then we have some, let's say some, so this is, let's say, this is W, WX, or W. All right. Then we have some point loads also somewhere in between. I mean, again, these point loads are also um, arbitrary. And you have maybe some P faults over here. All right. Okay. So let's label the support A. No, I prefer to, let me do this one A, B, C. Okay. Because those are the critical support I want to look at. So I'm labeling the mid support ABC. I don't need to label the outside supports per se because of the fact that I'll not really be using that much with my computation. All right. So with this being my beam, I want to look at some section of my beam. Okay. So I want to focus on the, so let me just again copy so that in your notes it will look nicer. Should this still work? Okay, great. Copy, and then we paste. Bring you down a little bit to the side. Okay. All right. So I want to look at this section right here. Let me just shade that portion. I want to look at this section. So I'm focusing right here, right in the space. Okay. Because that'll help me to easily formulate my equation. Okay. So that's what I'm looking at. Yeah. I think I can become a very good artist. I know how to shade. All right. So this is what we have. So I can draw that part out, and then I'll end up with something like this. Let me see if it's going to work again. Okay. So let me use this type of eraser. Let me use a small eraser. Yeah, this is cool. Okay. So this is going to take forever. Okay. Okay, great. So I end up with something like this. Okay. Yeah. So because A, B, and C are interior supports or interior members of a beam, from our days in basic structures, anytime you cut a section, you introduce moments. Okay. You introduce moments on these sections. Okay. Or you introduce moments, reactions, and I mean, you introduce all of these. Okay. You introduce all of these. But then our interest here is just to focus on the bending moment for now, the internal moments. So let's call this, okay, let's not give it a name now. We'll give them names later. Okay. So actually, that's what you experience anytime you cut a section. Okay. So let's say the length between, so let's find the length between A and B. and the length between B and C. So the length between A and B, let's call that length L1. The length between B and C, L2. Oops. L2. And then let's say the moment of inertia between A and B is I1. And then between B and C is I2. Okay, so the I here is the moment of inertia, which I believe you should know that by now in your strength of materials class. Okay, all right. So this is W, X. All right. So based on that, I can look at just this portion, the portion between A and B, and then draw, what's the name? Draw the elastic curve for that point. Okay. All right. So we end up with, again, these are my supports. Oops. So these are our elastic curve. Oops. I don't like this eraser. Okay. Let me change the eraser to stroke. Okay, great. And let me draw it again. All right. So let's look at this as it looks a bit funny, but this is the best I can draw. Um, let me try it again. All right, this looks better. All right, so if I draw a tangent, okay, so let me draw a tangent from, so I'm drawing a tangent, okay, another tangent, this tangent will be a bit off because my curve is funny. All right, let me just draw it out. No, this is not working. Okay, I think this is fine. All right. Um, all right, great. So this is tangent, best to use black to write. So we have tangent B. This is tangent again B, okay? And then we know that the slope here on this side and the slope on this side, this is theta BL. We have already mentioned that this is theta BR. All right, BL and BR, where L stands for left and R stands for right. Okay. Just so that we know. And then the going back to our moment area method, the vertical deviation, if this point is A, this point is B and C, the vertical deviation of point A when a tangent is drawn from B towards A, then it means that that tangent here will be T A B. Okay. Then in the same vein, the vertical deviation of C when you draw, oops. Yeah. When you draw a tangent from B towards C, that's TCB. Okay. This is from our days in the, what's the name? Our days in uh, the moment area method, okay? And then we know that I want to write one thing. Should I write it now or later? Okay, we know that theta So there are a few equations that we can look at here. We know that, or we have established that due to continuity, theta b left plus theta b right is equal to 0. So that's our first equation. Then the second equations, or the second and third equations, is that theta b left will be equal to TAB over L1. Okay. And then the third equation will be that theta B right will be equal to T CB over L2. Okay. So it means that if I'm able to find TAB and I find TCB, or the vertical deviations of these various points using the tangent, then when I sum these two together, that should give me my my equation. So pretty much find TAB, find TCB, then use that to find your theta BR and find theta BL, and then sum these two up into the above equation. That is the general derivation that we are looking at. Okay. All right. So we'll come back to this sets of equations very soon. Okay. So here, now, if you look at the general loads, so let me call this the general loads. Okay. And there's the elastic curve, or the deflected shape, whichever one you want to go with. Okay. We can convert these general loads into a case whereby we could look at a few things. So normally, let me again take this. Okay, I'm bringing it here. All right. So let's say, assuming we do analysis, some analysis of this. Let's say we do, let's say after some analysis, I have these lines to guide me to write properly yet. I'm not using them. So let's assume that we have done some analysis. Okay. So after the analysis, we end up with so we have these support reactions. What color can I use for that? Okay, so let me just go with the with this. Okay, I don't have another color to go, so let's still go with the blue. So I have the support reaction. I have, let's say, VA. I have the support reaction. So I'm going to make. I'm going to take away some extra information. I mean, some information that I already have, so that it becomes less. I mean, easy to see. So this is VB. And we also have VC. Okay. So the moment at these ends will be MC and also MA. Okay. And then there'll also be moments at, if you have to split this into two, there'll be moment at B. So you have moment, oops, I shouldn't use this color. Let me just go with a blue again. There'll be a moment here, MB, another moment here, MB. Okay. So this will be the support reactions. Okay. So these are the support reactions. All right. Typically, if we're trying to break what the reactions are. So even at B, even though we have MB going towards one on the left, the one on the left is counterclockwise, and then the one on the right is clockwise. If you sum them up, you get 0. right? Okay, you know. So these are the reactions that you'll find on a beam, right? I mean, so this is more like a general idea. In most cases, it's not all that you'd end up with. You end up with some, but not all. Okay. So if you have a case like this, okay, and you want to analyze it, it is easier to break this into different components. Okay. So you can look at the case whereby you have only the what's the name? The only the bending moment. So you have only the so let's say I can convert this into, so let me put an equal to sign over here. So this is equal to, you can have a first case here. So let me just draw the line again. So I'm going to draw a few things. Let me just draw one here. And draw another one on this side. Hopefully they have the same length. If they are not, please forgive me. Okay. All right. So this equation here, oops, let me just use the red again. All right. So we're using the principle of superimposition, all right, whereby if you are given a problem which is large, you could break it into parts, solve for the different parts, and then sum them up later all together at the end. Okay. So we can look at the case whereby we only have the or we have bending due to only the bending moments. Okay. So we have these bending moments. So we have MA, we have MA, MB, and then MC. Okay. Then, so this is only due to the moment, the, what's the name? Bending due to, so let me call this, is, why does this thing appear? Okay. So, bending due to, due to moments, okay, or bending moments. I don't want to make it look like it's tautology in a way. Then we have the case whereby we'll have the external reactions and then the external loads. Okay. So we have these external loads. Okay. Okay. So we want to derive equations for the slopes, okay? And then the slopes from our moment area method, as we looked at, slopes can come from the bending action, and these bending actions can be contributed by different loads, all right, or different behaviors. So in this case, we are looking at the bending action coming from the moment alone, which is the one on the left side. Then we are looking at the bending action also coming from the loads and then the supports, the vertical reactions. Okay. So basically just rewriting all that I have here from the beginning. Yeah, this is P1 and P2. Okay. So this is when we subject to when this is subjected to external loads. Okay. Okay. Because moments are the ones that will cause bending, and also loads will also cause bending. All right. When you read some texts go further and then also add bending from support settlement. All right, but I kind of think that that would be too broad for us to deal with. So I did not put in settlement in my derivation. All right. So you might go through some textbook and you find a very long equation which includes settlement of the support as well. But here we are assuming that there are no settlements, so we are making our equations fairly straightforward. Okay. So what it simply means is that this bending or the elastic curve will have two of them, one for the case due to moment and one for the case due to external loads. All right. So in a way, let me just redraw. Let me just bring this over here so that it helps us to appreciate what I'm trying to do. So I can, let me draw. This is too big. Can I reduce the size? Okay, I can. Let me put you here. I think this is too big, a little. Okay, this is fine. So if you're looking at it in terms of due to bending, that means that we'll have theta B L1 and then theta B R1. Okay, so that these are the rotations or the bending that will occur due to only the bending moment. Okay, then on the right hand side, I can also have something similar, which would be so then this becomes also plus. So I have bending. So if I look at only the external loads, then we have bending here. So this becomes TBL1, TBR2, sorry, theta BL1, and this is TAB2, and then TCB2. What this simply means is that the whole of theta B L is simply theta B L1 plus theta B L2. Okay, that's the idea. Then we can write the equations for the other portions. Theta B R is simply theta B R1 plus theta B R2. Okay. Then for the others to TA B is simply T AB1 plus T AB2. Then TAB, oh, TCB, sorry. TCB is equal to TCB1 plus TCB2. Okay, so that's the idea, all right? So we can derive the bending moment diagrams for all of these because we know that if you want to find TAB, which is the second theorem from the moment area method, it says that it is the moments of the M over EI diagram. Okay, so we need the M diagram, which is the moments diagram, divided by the EI and find the moment of the M over EI diagram. Okay. So in the case of only the bending, this is how our bending moment diagram will look like. So now I'm drawing the bending moment diagram. It looks like it looks somewhat like this. Okay. So this is MB, MC, MA. Okay. Here we are assuming that all our moments are positive. Okay, so that's like I have as I can have MA, MB, and MC being sagging moments. Okay, sagging moments are positive, or moment that will cause the beam to bend inwards or downwards, and they're called sagging moments. Okay. Then in the case of in this second case, here, we don't really know how the loading will look like because our loading is arbitrary, right? So we can just assume some arbitrary bending moment for it. And then this is how the shape of our bending moment will look like. Oops, don't change the color. Okay, great. So it looks like this, something like that. This is too big. So we don't really know what values are. So we could just say that this is called A1, this is called A2. And then the distance from the centroid of A1 to the outer section, let's call it X1. And let's call this one also X2. Okay. So the X1 and X2 are the distance from the centroid of my shape to the outer edge. Okay. We know that so we have these dimensions already. We already know what these dimensions are in terms of the length. So here, this is L1, I1, L2, I2 is the same on this side too. Okay. So L1, I1, L2, I2. Okay. So if we want, we first need to find TAB. Okay. So to find TAB, T. So let's go with finding TAB. TAB or is what is the is the moment of the M over EI diagram. Right, so that's what basically between A and B. Okay. And now here we take taking moment about A. Okay. So basically I'm using the area moment equation method or the area moment method to explain
Hello, sir.
three moments method. Yeah.
Please, why is the moment, the diagram of the bending due to moments? Why is the diagram like that? And then why is the one?
Trapezoid. Another one is like a semicircle.
Yes.
Okay. So um to explain that, so these are what we call point moments. Okay. These are point moments. MA, MB, MC are point moments. Okay. So for example, if I have a system whereby, let's say I have this moment, let's say this is 20, and maybe trying to make sure that I don't put some wrong info, and maybe this, let's say 40. Okay. Then it means that because they are point moments, when finding the Venn moment diagram, at every point, assuming my reactions here are 0, okay, let's assume that reactions are 0 for now. Okay. If I'm drawing my Venn moment diagram, let's say, so this is A and this is B. So because this is a point moment, the Venn moment at A will move from 0 and then jump straight to 20. All right. Because it's a point moment, and that's how we do with point moments. For example, if you have a cantilever, okay, you have, let's say, a load of 20 kilonewtons on it, you'll find, and this is, let's say, 4 meters. Your moment at this point is what? Your MA here is equal to what? 20 times 4, right? And that will give us 80 kilonewton meter. So this support moment, MA, is actually a point moment. And that's how when you're drawing your Venn moment diagram, it has this kind of shape. Okay. Because the moment here is a point moment. Okay, and that's what we have over here. So in the same way, we are looking at these points moment MA and MB. And if there's no load between A and B, pretty much what this means is that normally this will not be 40, this will might still end up being 20. So normally you between A and B, at any point between A and B, the moment is still 20, and it comes all the way down to 0. So this becomes the bending moment diagram when you have a point moment. Okay. So in the case whereby, let's say in my case whereby, let's say maybe this is about 30, then it means that as I move from A to B, there'll be as I move from A to B, there'll be an increase, slight increase all the way to 30. Okay. So these are points moments, and that's how we do the minimum diagram for points moments. Have you ever or have I ever given you any questions to try on that has a point moment in there? Technically, yes, I have, because anytime you do any cantilever beam, you are dealing with points moment. But like, let's say, have I given a beam like this? Then maybe put a load and then put a point moment in there, let's say 20 kilonewtons. And then 20 kilonewton meter, maybe this is like 5 kilonewtons. Have I ever done something like that? Normally, this will be our bending moment diagram for such a case. It might have something like this, pretty much. Because of the fact that because of the bending moment, there's a vertical whatever in the moment. I can explain this a bit more further for you guys. If you want us to have some 1 hour tutorial session, I can explain further why these things are what they are. Okay, because the assumption is that you've done basic structures, so this should be okay for us. In the case of the second option, it's not a semicircle that I'm drawing. I'm just drawing any shape. All right, so it's just a shape. Okay, I don't know the area of that shape, so it might even look maybe something like this. It's still a shape. Okay, I just don't know what that shape would be, so I'm just assuming that it looks like a semicircle. Okay, all right, and because we place the redundant or the moment on this side, that's how come at B here, the moment at B will be equal to 0. Okay, we'll get to understand this a little bit more as we go along. Okay. Let me take this one off so that it doesn't, just an aside. I don't need that here. Let me delete. Okay. So TAB's moments of the M over EI diagram. The M over EI diagram, where we find the moment between or we find the area of the diagram, and then we find the moments of that area between the points of interest, okay, about, in this case, A. So here, this is what I do. So in that case, if I want to find TAB, then it means that I need to, so for TAB, I need to find the moment with respect to this section. Okay. So I need to find a moment with respect to this section right here. Okay. So this will be one of my areas to deal with. And I also need to find this area too. Okay. So this goes with the TAB. All right. So let's continue. So it's the M over EI diagram. So let's start with which approach should I go with to make things easier for us? Okay, so let's start with the left side. I can divide this into 2 to make it easier for me to do my computations, okay? So from our moment area method, my M over AI diagram, in the first case, it becomes...
You gotta go back. Are you carrying the system? Well, that's carry it. Just carry the chair.
Okay, all right. So it means that I'm dividing everything here by EI, so I can bring that one out of the equal to sign. In this case, I'm looking at I1 because I'm focusing on the sections between A and B. So that's where the I1 L1 is, between A and B. So E over I1, I'm assuming that the E is constant throughout. So this will multiply that. So the first area will be MA times L1. Okay, so this will be the area of this rectangle right there. Okay, so that's the MAL1. Then this is multiplied by, since I'm taking moment about A, it means that it will multiply by about half the distance of L, so times L1 over 2. Okay, so this is the moment of the M over EI diagram from the moment area method. Okay. Then plus, now let me deal with the rectangle at the top here. And that rectangle would be half base times height, right? So the height would be MB minus MA. Okay, so this height over here will be MB minus MA. So let's say that is divided by 2 times a length of L1. Okay. Then from the centroid of the rectangle, from the center of the triangle to the base here, or to A, will be 2/3 of L1. So 2L1 over 3. Okay. So I'm done with the left side of the case, the option 1. Now I come to the right side, or I come to the case whereby we only have the load. So I come to this point right here. Okay. So it becomes plus, I don't know what the area is, so I can just say A1. Okay. So the area of this shaded portion is A1, and then the distance from the centroid of A1 to A is X1. Okay. Pretty much I'm done with this. Okay. So this becomes TAB. Okay. So I can expand TAB to write it in a nicer format. So TAB would then be equal to, again, 1 over, I can bring the E out, or should I say, okay, let me keep the both the E and then the I out. Okay. I don't know why my mouse keeps moving. Okay. So here I can expand it. I'll get MA, M sub A, L sub 1 squared over 2 plus, so let me expand this. Okay, if I expand it, I'll get MB or M sub B, L1 squared over 3. Am I correct? I think so. Okay, I think I'm moving up a little bit. It's fine. It's okay. Then minus MA or M sub A L1 squared over 3. Okay, it's 2 over 6. So 2 over 6 is 1 over 3. All right. Then plus A1 X1. Okay. So we can see that I can summarize this into, again, 1 over E I sub 1, bracket open. So let me bring the A1 X1 forward here. It doesn't really matter, A1 X1. I'm just trying to rearrange everything. Then I can subtract. So you can see that this one, the first term here, okay, the first term here, and then this other term here, I can add them up, okay, because they are both the same. All right, so MAL1 squared over 2 minus MAL1 squared over 3. And then when you do the computation, you will get M sub AL1 squared over, is it 6? Yeah, I think it's over 6. All right, then plus MB L1 squared over 3. So this becomes your TAB. But what we have interest in is not TAB, but actually theta B on the left. So actually we want to find theta BL. Okay. And theta BL is the same as TAB over L1. So pretty much dividing everything through by L1. Okay, so that's the idea. Okay. So if we do it that way, like I said, you can have 1 over E, then bracket open A1 X1 over L1 I1. Okay. Plus M A L1 squared over 6 L1 I1. Okay. Then plus MB L1 squared over 3 I1 L1. Okay. So again, we can do a bit of, or we can move things around a little bit. Let me just move this towards the right a little bit. Yeah. Okay. Then move you again. Let's try to save space. No mind me. Okay, so I think this is fine. All right. Okay. So then this then becomes, I can have 1 over E again. Then I can open the bracket. So A1 X1 over L1 I1. Then here we have plus MA L1 because they'll cancel out over 6I1. Okay. Then plus M sub B L1 over 3I1. Okay. So this becomes right here is our equation for theta BL. Okay. So we can also come back and do something similar for theta BR. So focus on the right side, this right side over here. Focus on these two right side because it's the, since we are finding TCB. Okay. So the next one is to find TCB. So again, let me just copy this here so that I don't need to write all of that. A lot of things have been copied, which I don't need. Okay, let's see. Oh, that's actually amazing. Okay, so the next thing is to find TCB. Okay. So let's say TCB. So the moment of the M over A diagram between B and C. Okay. Taking moment about C. Okay, so that's the major difference. Okay. So you will see that whatever I did for this first one will be very similar with respect to the second one. Okay. So to save time, I'm just going to copy and do the editing, just explain to us what is happening. Okay. All right, so here we'll have m sub c. So we have m sub c times L2. So it also becomes, let me just delete these things. Okay. So m sub c, so this becomes I2. Then the height over here will be between MB minus MC. All right. So the height of the second triangle or the right of the triangle on the right will be MB minus MC times L2 again. Since we are finding moment about C, then it becomes 2/3 of L2. Then on the right side also we have A2 X2. Okay. So it becomes A2 times X2. Okay. You can see that they look very similar. Okay. So again, I can expand all of these. And then once I expand, I'll end up with these interesting equations. Let me just put it here. So again, going to do a bit of editing, nothing strange. Everything looks fine, I believe. Yeah, so let me just do the editing so that we'll come back and then so I take you off, I take you off, I take you off. Just take these guys off. Okay. Okay, just take you off, take you off. Okay, so there's a bit of erasing and working my way through some of these things. It shouldn't take too long. Okay. Yeah, I think I'm good. Okay, so just go back here. I'm just trying to expand this. So I get MC, so this becomes I2 MC L2 L sub 2 squared. Then I get my MB. Oh, I didn't take this guy off. Okay. All right. So MBL2 squared, then this becomes MCL2 squared, then A2X2. So if I do my expansion, and I do my additions and all that, it becomes A1, A2X2 plus, so yeah, I get MC L2 squared, and then I get MB L2 all squared over 3. Okay. So again, theta B, this is C. So theta B on the right side will be TCB over L2. Okay. So if you multiply through by, or if you do the computations, you end up with A2 X2 L2 I2. Here too you get MC L2, then L2 I2. So something like this. Okay, they look very similar. All right. So in some cases, if they are considering settlement, these equations will be a bit longer than what we have over here. Okay. So I can again end up with A2X2, I2, L2. One of them should be L, and one of them should be I. Okay, so let me just do this thing properly. So L2, and this is MC L2 over I2, then MB L2 over I2. Okay, so we have these two equations that we need to deal with. Okay, so so this is equation 1. So this is equation 1, and this is equation 2. Okay, so we sum them up. Okay, so that's the idea. We sum up equation 1 and equation 2. Okay. So let's think hopefully I've covered everything. Sum up equation 1, equation 2. So yeah. So AX L2 over I2. Yep. I think this should work. Something I'm looking for, but I can't seem to find it. I think it's this one, maybe. Okay, yeah. So we know that theta B L plus theta B R equals 0. Okay, I mean we've done that already, so I can just take whatever I have for equation 1, copy that, bring it here, and paste that. Okay, I have that information already for then also have this for the other one. So again, copy and then paste. Okay, it makes it easier to just move things around. And let me just put a plus here. Okay, so let me see if I can delete the what's the name? Okay, great. This one will be a bit challenging. Okay, now I'm over deleting. Yeah. Sometimes this happens when you. All right, so I'm just write it again. I have this here. A2X2, oops. And then I2, L2, MC, L2, MB. So all of this is equal to 0. Great. Okay. So we can expand, I mean, or multiply through by E. So let's say we multiply through by let's say 6E. Okay. So multiply through by 6E, which means that we are going to end up with A1X1. So let's say 6A1X1 over L1I1 plus MA L1 over I1 plus 2MB L1 over I1 plus 6A2X2 over I2L2. Okay, let me just get it right. What's wrong with my screen? Seems to be moving a lot today. I2L2. Okay. Sometimes my I and my L, they look very similar, sorry. Then plus 6MC L2 over I2 plus 2MB L2 over I2 equals 0. Okay, this is easier to work with. So what I'm going to do is that I'll move the...
Hello, sir.
Yeah, hello?
For the MCL2 over I2, will the 6 not cancel the 6 down there? If we're multiplying through by 6a,
Okay, sorry, it's a mistake. All right, thank you. Yeah, thank you.
and I guess the first okay, yeah, okay, it's correct. I'm sorry.
Yes, correct now. Yeah, I think, yeah. All right. Okay, great. So we have this now. We can simplify it a bit further. So what I'm going to do is I'll end up with, so let me do the MA. I'll end up with MA L1 over I1. Okay. Then I'll get 2MB L1, oops, over I1 plus 2MB L2 over I2 plus MC L2 over I2. And this will be equal to minus 6A1 X1 over, let's say I1 L1, then minus 6A2 X2 over I2 L2. All right, so I'm just trying to make things easier. So that's all the external moments, or the bending due to moment is on one side, and then the bending due to external loads are on the other side. Okay. So here, my equation then simply becomes MA L1 over I1 plus 2MB into brackets L1 over I1 plus L2 over I2, then plus MC L2 over I2, and this we could have minus 6 into brackets A1 X1 over I1 L1 plus A2 X2 over I2 L2. Okay. Yep. And ladies and gentlemen, this becomes the equation that we'll use to calculate our moment. So this becomes a 3-moment equation. Yeah, it seems long, I know, but it's fairly straightforward to use. Okay, so here we have means that it will be easy to find with this one. Mostly our unknowns or our redundants will be MA. So our unknowns will be MA, MB, and then MC. So MA, MB will be the unknowns. Okay. So the equation initially will be used to find these unknowns, find MA, MB, and then MC. Okay. Now, a simplified version of this equation would happen. So let's say the case where I1 is equal to I2 is equal to I. So if both sections of the beams have the same geometry, all right, which means that they will have the same moment of inertia, then our equation here will reduce to simply so to become MA L1 plus 2MB. Let me write that in a red color. I don't know if that should work. So let's see. So we have MA L1 plus 2MB or M sub B L sub 1 plus L sub 2. Okay, plus MC L sub 2 will be equal to minus 6 A sub 1 X sub 1 plus A sub 2 X sub 2. Okay, so this, sorry, sorry. This is over I1, sorry, L1. Over L1, this is over L2. So this becomes a simplified version of the equation where the moment of inertia is the same throughout. So if it's the same throughout, then this becomes the simplified version. But then if it's not the same, then you have to go with a more general approach. Okay. So as I explained earlier, that this equation is used for two sparks at a time, or three, what was the name? Three support at the time. So some books, what they do is that in order not to confuse us in terms of these, the A, B, and C, they assume that A here is the left and B, so A is the left. So let me just say that some books go with the fact that, okay, let's say A is the left, which is, let's say, L, then B is the center. Okay. So that will be center C, which is a bit funny. Then my point C would then become my right. So it becomes R. So you can see that some books will just take this equation to maybe just rewrite using the simplified approach so that I don't need to write this whole thing again. So some books will just go with this. So instead of MA, they will end up with maybe these, just so that they feel like some just feel like that will help them to appreciate the equation a little bit more. But the key thing is trying to understand what these terms are. So maybe you can have M left plus M center. So L left, L right. This is M right. This is left. Okay. M right. Then this one, what do you do? A right, A left? Yeah, maybe. A left, X left, A right, X right, and then L left, L right. Yeah, I mean, this is a bit funny for me. So mostly I just prefer to use the A, B, C. But sometimes the students don't understand what the A, B, C is, in the sense that the A, B, C is not necessarily the points A, B, C all the time. It's more about the what's the name? The beam under consideration. So let's say if we go back to our very beginning right here, okay? So if you take span A, B, B, C, then fair enough, your equations becomes MA, MB, and MC. So with the B as being the center. But if you use span BCCD, then you're looking at MB, MC, MD. So what used to be your MA now becomes your MB, and what used to be your MB becomes your MC, and then it goes on. Now, if you look at span CD, it becomes MC, MD, so it becomes MC, MD, ME. The key thing is that these are the centers, or these are, so the ones here, so this is the center. So these are the center. This is the right side, and this is the left side. All right, so that's the best way I think I can explain this. All right. We end at is it the next 1 hour, right? Okay. I think I've been talking for some time now. Okay. So let's take some 5 minutes break and then we'll meet up. We'll just so just stretch your legs a little bit for about 5 minutes, stretch your legs and arms and your eyes and head, and then we'll meet back here. All right. If you have any questions, I'm around to answer them for you. All right, so let's look at what we have to do. So let's go straight and look at some examples to help us appreciate the process involved in using the three-moment equation method. All right. So let's go straight to an example. So let me call this example 1. So with example 1, I have a beam. That is my beam. These are the supports. Okay. So this is A, B, and C. So we have these loads on it. So there's a UDL between B and C. Okay. So this is 1 kilonewton per meter. The length between B and C is given us 4 meters. And between A, I always forget to change my eraser. Okay, yeah, this is better. So between A and B, we have these dimensions for the length. This is 2 meters here and 4 meters. And there's a load, a point load right there, which is 3 kilonewton. Okay. So here we are to draw the, let me just write it on the left. Draw the bending moment diagram and shear force diagram. Okay, so I have to draw these two diagrams. Again, this is a continuous beam. The number of unknowns are more than the 3 equilibrium equations that we need. And this means that we cannot solve them using our basic structures knowledge, all right, from first semester. So what do? We know what so here EI is constant. So EI is constant. Okay. All right. So steps 1, let's say, so there's a solution. So we start with step 1. So we draw the bending moment. Bending moment diagram. Or let me just say BMDs. All right. Bending moment diagrams. Assuming simply supported. I'll explain what I mean. Assuming simple support or simply supported is fine. Yeah. Simply supported beams. Okay. So here we treat the spans as though they are simply supported. Okay. So if I take span AB, I know B is an interior support, all right. But then I treat AB as though B is simply supported. Then I draw the bending moment diagram for that. Okay. So if I'm to do that, I'll end up with so if this is A, B, and C. This becomes my bending moment diagram for AB. Okay. So I'm assuming that AB is simply supported. So here the assumption is that I take, so I have this 3 kilonewton load just like that, and this is A and this is B. Okay. Then I know my supports, So these are my supports. So this is B. These are the supports A. I have my dimensions 2 meters, 4 meters, and I draw my bending moment diagram. Okay. So this is how the bending moment diagram is going to look like. Okay. The highest value here, again, as I've mentioned a few times, the goal is not to draw these bending moment diagrams. So we don't have to spend too much time on it, and we need to figure out shortcuts to draw these bending moment diagrams. Okay. If you have a load, let me just do that over here. If you have a load, and this is P, okay, and then from the left end to P is A, and then from P to the right end is B, your maximum bending moment is PAB over L. Okay, so here our PAB over L, let me just put it down here so that so PAB over L will be equal to our P is 3, our A is 2 meters, our B is 4 meters. The entire length of section AB is 6 meters. So if we do that, our bending moment max here is 4 kilonewton meter. Okay. Then the other option, let me see if I have to go. Okay, I can go towards the right a little bit. Okay. So the oops. Okay. So here we have the other case. If you have a simply supported beam, let's say W, with these at the ends, let me just make this one so that it looks determinate. This becomes our bending moment. Okay. The maximum bending moment is WL squared over 8. The max at the top here is WL squared over 8. This one is PAB over L. So I can draw my bending moment diagram for BC, and it might look like this. Let me draw something shorter. Okay, great. So here it means that WL squared over 8 will then be equal to our W is 1, L is 4 meters, so 4 meters squared over 8, and that will give us 2 kilonewton meter. Okay, so the maximum value here is 2 kilonewton meter. Okay, so we have some information that we need. Now we can go ahead, and then so I can treat the left side as area 1 and treat the second one as area 2. Okay, so now let's find area 1. So draw the bending moment diagram. So that's the first step, which I have done. Now, step 2 will be to find the variables used in the equations. In the 3-moment equation. Okay. The 3-moment equation. Okay. All right. So the 3-moment equations, we have A1, we have X1, A2, X2, and all that. So we'll find what they are. Okay. A1 is simply the area. A1 is simply the area of the moment diagram on the left. Okay. Then the A1 has a corresponding X1. So here our A1 will be I prefer to divide my triangle into two because this is not an isosceles triangle. Yeah, it's not equivalent, nor is it isosceles. So I think it's scaling and it's easy to divide it into two because of the fact that I'll need different x values. So I can have the left side and then the right side. Okay. I mean, the right here has to do with here, the left has to do with this whole space here. Let me just shade it so that we know this is the entire left. Okay, so A1 is the entire left. So the left is A1 is the entire left. Okay. So A1 will be half times 4 times 2. Okay. Plus half of 4, where 4 is the height, times a base of 4. Okay. So this will give me a total area of 4 plus 8, and that'll be 12. I mean, if you want that. Okay. Now let's find the x1. Okay. Because the triangles are different, it means that the x1 will be different. All right. So the x1 for this portion here, and the x1 for that portion over here. So the x1 for this portion would be, since we are finding moment about with respect to A, because that's the idea behind the three-moment equation. So this becomes 2/3 of the base 2, and then this other portion becomes, so let me use n because we are not adding per se. Okay. Then this one becomes, so even in that case, I'll just delete this right here so that it doesn't confuse us. Let me leave it as it is for now. Then for the second part of the triangle, it becomes 1/3 of the base 4 plus 2, because again, it's moment about A. So this is like, you find this here, then you find that here too. All right. So maybe this is x1, 2, this is x1, 1 kind of. Yeah, I don't want to be doing that to make the work a little bit too much to do with. Okay. So it means that A1, x1, this whole thing here, this goes to 4, and this also goes to 8. Okay, we have already established that. So A1, x1 is simply 4 times 2/3 of 2. Okay, plus 8 times 1/3 of 4 plus 2. Okay, so this is the A1, x1. Okay, so you don't sum all A1s and then sum all x1 before you multiply. No, it's called its moment. So the moment of each section, which is the load or the area, times their respective distances, perpendicular distances in this case, about a point of interest. Okay, so this will give us 32. Okay, if you want, the unit is 32 kilonewton meter squared, I think. Oh, no, it's more than that. I think cube or so, yeah. So cube, okay, if you want a unit. So now that becomes our A1, x1. Now let's find our A2, x2. So A2, which will be equal to the area of the moment diagram on the right, or on the right side. Okay, so I'm showing that with a green here, A2. So this will be A2. Okay, so in case you can use the color coding to indicate which is which. So here again, and this will be equal to the area of the, in this case, the semicircle, right? Which is 2/3 of, so we should know the area of some of these shapes. So 2/3 of a base of 4. Oops. 2/3, geez, this is moving a lot. 2/3 of a base of 4 times the height of 2. And this will give us 32/3, maybe. Am I correct? Yeah. Then our x2 here will be half of the base because this is a semicircle, so it becomes half of the base. So half of the base, and no, I don't think so. Let me just check it over here. 2 times 4 times 2. So it's 16/3, sorry. 16/3 here. Half of the base will be 2. So it means that a1 x1 will be equal to 16/3 times 2, and that'll be 32/3. Okay, so now I know my a1 x1, my l1. So again, l1 will be the length of AB, which will be equal to 6 meters, and L2 will be the length of BC, which is equal to 4 meters. Okay, I1 is equal to I2 is equal to I. So we have established all of these unknowns. Okay, so I can use my, I think the third equation, I mean the simplified one, because that's what I can use a simplified version to just solve that. Okay, so let me just add this. Okay, so this is what we have. Okay. So now let's put in the parameters. So it becomes MA, L1 is 6, so MA times 6 plus 2 MB, 6 plus 4 plus MC into brackets 4 minus 6 bracket open A1 X1, we got 32. So 32 over L1, where L1 is 6 meters, plus A2 was given as 32/3. So that's 4. So this becomes your equation. Okay. So there are 3 unknowns. We need MA, we need MB, we need MC. So if there are 3 unknowns, we need more than one equation to solve them. Okay. But this is one of the special cases, or should I say many special cases. We already know what the moment at A would be. Okay. Since the supports at A and C are simply supported, or they are pin supports or roller support, and then we know that pin support and roller support at the ends of beams have 0 moment. Okay, so it simply means that our MA is 0, our MC is also 0. So this portion and that portion can cancel out. So we'll end up with 2 MB times 10, which will be equal to minus 6. We can sum everything within the space here, and this will give us times 8, I think. We can do the math and see. It should give us 8. Okay, so in the end we'll end up with 20 MB being equal to minus 48. Okay, so our MB, which is the moment at B, it's minus 48 over 20. That'll give us minus 2.4 kilonewton meter. Okay, so pretty much we found our moment at B, which is minus 2.4 kilonewton meter. Okay, but that is one part of the solution. All right, we found the redundant moment, so we found MA and MC are 0, and we've also found MB. But we need to draw the shear force and bending moment diagrams. Okay, so maybe I should put here step 3. So this is step 3 here. solve for the unknown moments. Okay. This might be longer than this, depending on the question that we have. We could have simultaneous equations, maybe double simultaneous or triple simultaneous equations. So it depends. But this is in its simplest form to explain the approach. This is what we are using. Okay. Now, so we have our step 3. No, this is step 3, sorry. I think so. Yeah. So now let's go to step 4. Find support reactions. Let me just. Okay. So the best approach when we're drawing the Benjamin diagrams, one of the assumptions we made is that we are assuming that the beams are simply supported. Okay, in the sense so that at B is like we break our continuous beam into separate spans or separate segments. Okay, so that it makes it easier to use the equation. Okay, so in the same vein, you could come here, have these. So this is AB and then C. So I'm breaking my spans into 2. Okay. So this is C. All right. So I need to find VA. I need to find maybe let's say VB1, and then find VB2, and then find VC. Okay. And then we found that the moment at A, let me just use a different color. So that was MA. So basically, this is how we had our initial problem, if you remember. So we have, and I think there was some points loads on it, and then the UDL. Okay, great. So this is what we had initially, right? Okay. The moment at A, so MA is 0, MB is minus 2.4, MC is 0. Okay, so this is MC, this is MB. Okay. So you can look at different spans. Okay, so the focus will be is to look at maybe the span on the left. So if I'm to take the span like this, does it work? Yeah, it works. Okay. So I bring it down below. Okay, so I have all of this. So this is minus 2.4. So these are MB, and then we have a load of 3 kilonewtons at the top here. Okay, so here this becomes simply supported. I can find my reactions. I can find VA and find VB1. Okay. So let's say summation of moment at B is equal to 0. All right. So it becomes, I think the distance here, this is 2 and this is 4 meters. Okay. All right. So summation of moment at B equals 0. So that implies that we have VA times 6 minus 3 times 4. And then the point moment will come into play. Okay. So the point moment would be minus 2.4. Okay. I will explain why that is the case shortly. Minus 2.4 equals 0. Okay. Now since we are taking moment about B it means that VA, or you know what? Instead of me using the actual values, I rather use the variables for now. So this is our MB. Okay. And this is our MA. So it becomes VA times 6 minus 3 times 4, then plus MA minus MB. Okay, it's easier this way. Okay, so with B as our pivot, VA will cause a clockwise rotation. The 3 kilonewton load will cause an anti-clockwise rotation, right? Okay. MA is clockwise. MA is clockwise. So let's see, it's the same as this guy over here. Let me just do it this way. Okay. MA is clockwise. MB is counterclockwise. Okay. So MB is negative, the same with the low because they are counterclockwise, and then the clockwise are positive. You can interchange the directions. It's entirely up to you. At least this approach helps us to appreciate what goes on. So I can delete this now. We don't need that. So here become 6VA minus 3 times 4 is what? 12, right? Our MA is 0. Okay, MA is 0. But our MB is equal to minus 2.4. Okay. So then this becomes minus 12 minus into bracket minus 2.4 equals 0. Okay. So let's do our computations and then we'll see what we'll get. So it becomes minus 12 plus 2.4. So that'll give us 14.4. So it means that our VA here is simply oops, that's it before. So it becomes 9.6 over 6, and that should give us I'm hoping I'm correct. What did I get? Do I remember what I had? I was hoping that I wrote that somewhere. Doesn't look like I wrote it anywhere. Okay, that's fine. Let me see. Okay, so that'll give us 1.6 kilonewtons. Okay, great. Okay. So from here, we can also find, we can easily find our you can find out VB1 because VA plus VB1 equals 6 kilonewtons. Okay, so this is summation of vertical forces about, equals to 0, not about any points. All right. So if VA is 1.6, then VB1 is equal to 6 minus 1.6. And that
Hello,
should give,
sir. Is it 6? Why is it not? Is it 6 or 3?
oh, it's 3. Oh, how come I'm writing 3?
Yep.
All right, so it's 3, sorry. All right. So that'll give us 1.4. All right. So VB1 is 1.4. Okay. So we are done with the first portion. We come and look at the second portion here, which would be my thing is misbehaving. Sometimes these things, yeah, they tend to act up. Okay, hopefully it's back to its senses. Doesn't look like it. Okay. Okay. Let's look at the second bit. Yeah, nothing copied. Nothing copied. Jeez. So this is far better. So let's see. So at this point, it becomes fairly straightforward to do in terms of the computation. So minus 2.4. Then we have, so this is B, this is C. Okay, so here again, we find so we do summation of moments about, let's say, either B or C is up to us, whichever one works for us. So let's say about C equals 0. So we have VB 2 times 4. This is 4 meters here. Okay, and then the load is 1 kilonewton per meter. Okay, great. So VC times 4 minus 1 times 4 times 4 over 2, which is 2, because it's going in the other direction. Then plus MB, because MB is the same direction as V2, then minus MC, okay, equals 0. But our MC is 0, we know the value of MB. So 4VB2 minus 42 is 8, then minus 2.4 equals 0. So VB2 would give us 2.6 kilonewtons, I think, yeah. So 8 plus 2.4 divided by 4, yeah, 2.6. So if VB2 is 2.6, then if you're summing vertical forces, it means that VB2 plus VC equals 1 times 4. So VC will be 4 minus 2.6, and then VC will be 1.4 kilonewtons. Okay, so our support reactions, we have VA to be equal to 1.6 kilonewtons. VB will be both VB1 plus VB2. Okay, so that will be 1.4 plus 2.6, and that will give us what? 3, right? So we get 3 kilonewtons. Is it 3 or 4?
It's 4, so
Okay, yeah, it's supposed to be 4. Right. So it's 4 kilonewtons, and then VC will give us 1.4 kilonewtons. Let's see if it makes sense. Okay. The total external load acting on the beam would be 3 plus 4, which is 7. All right. So if the external load is 7, that means that my reaction should all add up to 7. Okay. So I have 1.6 plus 1.4 plus 4, and that is also 7. Okay, so I'm correct. Great. Okay, so now we have the support reactions. Okay. There are a number of ways to draw the bending moment diagram or the shear force diagram. Okay. If I'm to use the original beam, which we had from the beginning, so this is what we had. Okay, so we have the UDL and then the point load somewhere, not at midspan, or somewhere here. Okay. So now we know our reactions. We know our VA, VB, and VC. This is 3 kilonewtons here. This is 1 kilonewton per meter. This is 1.6 kilonewtons for VA. VB is 4 kilonewtons, and then VC is 1.4 kilonewtons. So from here, we can draw our shear force diagram, all right? Because we have all our unknowns. So our shear force diagram would look like this. So it starts off. So it goes to 1.6. Then between that point and then the load comes down to minus 1.4. And it maintains that minus 1.4. 1.4 should be smaller than 1.6, right? Okay. So it goes to 1.4 all the way straight till it meets the UDL. Then it jumps to 2.6. Okay. Then we have this. Okay. So this value here, the value here is 1.6, 1.4, 2.6, and then 1.4 again. Okay. I mean, I'm to assume that we cannot draw shear force diagrams. Okay. So 2.6. All right. So here is the positive phase. And then we have below the negative phase, then positive again, then negative here. Okay, so this becomes our shear force diagram. Okay. The next will be to draw the bending moment diagram. So again, let me just move the ruler down here a little bit. Let me just draw it on the side. Mostly it's best to draw these things below. Let me just draw it below, so I don't have to bother myself with. Okay. So that's what we have. There are a number of ways to draw the bending moment diagram. Okay. So we'll do so I'm taking you guys through the first approach right now. Okay, so with the first approach, if you have all your loads acting on it in this way, it's what we are used to. So at A0, at B, the bending moment is 1.6 times, sorry, I didn't say B. So let me call this one A, B, C. Then let me call this one K. Let me call the midpoint of this as maybe M. Okay, so this is K, B, will this be at the center? I doubt. I think to be honest, let me just take the M out because it might be confusing. So just let me use the A, B, K, and C. Okay. So at K, our moment becomes 1.6 times 2. Okay. So that'll give us a 3.2. So that's it's not anything strange. So this is 3.2 somewhere here. Okay. So I have the straight line 3.2. Okay. Then at B, it will go all the way to so this is 3.2. At B goes all the way down to minus 2.4. Okay. So this becomes minus 2.4. So let me just put in 2.4 here. So that's going to be a straight line. Sometimes you want to, okay, let me just use the ruler to draw these lines just so that they look nicer. Okay, so this is fine. And I draw another one. Oops. Okay, I think this one looks cool. Yeah, it's better this way. Okay. Then between B and C, You have, I think, this should be our maximum points. That should give us what did we get earlier? That should give us 2, eh? So we should get 2 somewhere here. Oops, we should get 2. Am I correct? It should be less than 2, eh? I can easily find that. Can I find it? Okay, let me just not bother ourselves with finding it. Okay.
Sir,
Hello?
please, what's the distance? What's the distance between A and B?
Oh, the distance between A and B. That's what? It's 6 meters. This is what we've been doing from the word go. This question.
All right.
Between A and B is 6 meters. Between B and C is 4 meters. Okay.
All right.
All right. So, oops, why am I in my info? So I'm going to show you guys how to do some of the, like how to find these values. There's 3.2 and these other things, okay? You can easily use your diagram here to find them. If you know where x is, this x over here is, you can determine this x, okay? Because they both will share the same value. Where the share is 0, there's maximum, what's the name? Moment, yeah. So in this case, it's what 1.4 minus 1 times x, right? Equals to 0. So 1 times x is equal to 1.4. So x is 1.4. All right. So the length is 1.4. So it becomes 1.4 times 1.4 times 1.4 minus 1 times 1.4 squared divided by 2. So this will give us sometimes when you know the value, you see how small things are. Oops. So actually, this is how it looks like. Okay. And then at this point is minus 0.98. Okay. So this is positive, negative, positive. Okay. So there's one way to draw the bending moment diagram, okay, without too much stress. There are other approaches that we can use to draw the bending moment diagram. I'll do that on the right side so that we would also see how that one works. Okay. I mean, whichever one you want to work with is fine. I mean, it's up to you to decide. Okay, so this works for everybody. I think the one on the left works for everybody. The one on the right, we can look at the separate portions. Okay, so I can take this here. You copy this and bring it to the side. So pretty much everything that I'm doing, just do them again. Doesn't really. So I know that my VA we go at 1.6, right? I think for V 1.6. VB1 we got 1.4. VB2 we got 2.6, and then VC we got 1.4. So now if I'm to draw the shear force, I'm drawing the shear force for. So let me just separate this a little bit. Just separate them. Just move them a little bit towards the right. Okay, that's fine. Either way, we still have our 2.4 minus 2.4 here. It's the same value for both of them, so it doesn't really matter. Okay. So now I'm dealing with the left side. I can draw the shear force for this, right? Shear force diagram for that. Okay, so I have this here. My shear force is simply, this is 3 kilonewtons. This is 1 kilonewton per meter. So my shear force, this is simply supported. So my shear force goes to 1.6. Oops. It goes to 1.6. It meets the 3 kilonewton load. It comes down to 1.4. And then I'm done with this drawing. Okay, so this is the other half. Okay. So this is the shear force diagram, bending moment diagram. Okay, so again, this is my shear force diagram. Okay. I also come to the one on the right. I don't know whatever happened on the left, so I don't care about that. So I come to my right, also draw my shear force diagram. Okay. Again, it starts at 2.6. Then because there's a UDL in there, it goes to 1.4. All right, so this is it. Okay. So here I have 1.6 and 1.4. You have 2.6 and then 1.4. So you can actually see, if you compare the two, you see that they are the same. Okay. The portion here, the portion here, the portion with the yellow shade is the same as the one on the left. I mean, these two. Okay. Then the portion with the green shade, okay, is the same as the one over here. Okay. So you can just then from here you combine these two. So you just add them together, or you just attach the two drawings together and they look the same. Okay. In the same way, you can also do some for the bending moment if you want to put them in different modes. So again, you have this. So this plus that will give us everything over here. Okay, so the plus sign will be equal to this. Okay, so it's pretty much the same thing. Then in this case, also our bending moment diagram will look like this. It's VA, so it goes to 3.2, then it comes down to minus 2.4. Okay. So this is our bending moment diagram. There's 3.2, and this is 2.4. All right. Then assuming you don't know whatever happened on the left, you do the same for the right. And then for the right, we have, we're almost done with it, and then we can end today's class. Then for the right, you have a minus 2.4, so that's a hugging moment, so that would be negative. Then your moment diagram, when you draw it, will begin to go this way, that way, and then come back to zero, with the maximum being 0.98. Okay, so again, if you add these two together, the left side is right here. Let me just put, okay, yeah, up to this point. Okay, which is the same as the one over here. And then the right side, which is something like this, is this point over here. Okay. So, and then once you add the two together, you get what you want. So this is also, again, 2.4 here, and this is 0. Okay. There's also another school of thoughts. Let me just show you that we can go. They are just, it's good to know the options available to you, and then we'll agree on the one we want to work with. When we look at the, assuming we are using the case whereby we separate them based on the moment and also based on the loads. Okay. So based on the moment alone, which is what we did in the beginning, we had A, B, and C. So we had these moments. All right. So we had our MA, MB, and then MC. We had these moments. Okay. So what if we draw the bending moment diagram based on only these moments? Okay. So we'd end up with so our MC was given as 0. Our MB was given as minus 2.4. Our MA is 0. Okay. So technically, our bending moment diagram for this particular beam would look like this, with this being 2.4. So this is negative. So this is for only the loads. I mean, only for the moment. Okay. Then the case whereby we had the where we had only the external load. Sorry, I think we had A, B, and C. So we had these external loads here. Okay, I'll go over this maybe next week, yes, but I just want us to have everything complete so that learning becomes easier. Okay, so this is 3 kilonewton, sorry, and this is 1 kilonewton per meter. Okay, and then we drew our bending moment diagram to look like this. Okay, so these were our bending moment diagrams initially. Okay, so these were our bending moment diagrams. If you remember from the initial computations, so we had here to be 4 kilonewton meter, and then we have 2 kilonewton meter. So we can actually superimpose these two. So we can add these two together, and then we'll get, once we add, then it will be equal to. So pretty much what we can do is that I have the beam again. I have, so let me do this one as red, since that one's negative. So negative 2.4. And I have my red on it. Okay. Oops, this is too much. Okay, I think it's fine. I mean, yeah. So this is what we have. This is 4 kilonewton meter, and this is 2 kilonewton meter. So this is acting at the center. This is not well drawn. Okay, this is better. Okay, yeah. But this makes sense. Okay. So this is positive and this is negative. And there are some points which are of importance to us. Point A, point K, point B, maybe the midspan of this, and then point C. Okay. So I can look at this whole thing here, this superimposed diagram, and then come up with a much more simple approach. Okay. And a much more simple approach would be at A, the moment is 0, whether it is a green moment or it's a red moment. But at K, where K is this here over here, we know that for the positive moment, K is 4, but then for the negative moment, we don't know what K is. So we can use similar triangles to find K. Okay. If 6 meters is equal to 2.4 kilonewton meter, then K is at what? 2 meters. So what do 2 meters give us? Okay, so that's the idea. Okay, so it becomes 2.4 times, if let's more divide, right? So this becomes 2.4 times 2 over 6. Okay, so that's the idea. So times 2 divided by 6. So K is 0.8. Okay, so at this point, so at K, we have plus 4 minus 0.8. Okay, and that will give us 3.2. So at K here, moment is actually a positive moment. So it's 3.2, which is the same as what we had over here. All right. Then if you go to B, at B, the positive moment is 0, the negative moment is minus 2.4. So it means that at B, we have 0 minus 2.4, so it's still minus 2.4. All right, so at B, it's still minus 2.4. So nothing really has changed. Okay, so we have again the straight line. Now, here, what happens is that we know the height at midspan. Okay, so the height at midspan, so let's call it, I can call this one M. So at M, at midspan, we know that the positive is what, 2. The negative will be half of 2.4, which is 1.2. So it becomes 1.2, and this will give us what? 2 minus 1, 1.2, 2 minus 1.2, and that will give us 0.8. Okay. So you can see that this has a little bit of difference compared to the other one. So again, if I continue drawing, because there's a UDL here, you can see that this is how it means that the entire diagram will be controlled by the UDL. Okay. So here I'm using 0.8. Okay. 0.8 is not the same as what?
Hello,
0.8.
sir.
Yeah.
Sir, please can you come again with the similar triangles of how you got K? Sorry, I don't understand it a bit.
Okay.
Just recap. Thank you.
Okay. So similar triangles. So if you have a shape like this, okay, and this, you know, this height h, so let's call it big H. So this height is big H, okay, and this distance is big B, okay. Now, if you want to find, assuming I draw another line here, and I want to find this height, this small h, and I know this distance B, then it means that per the rule of similar triangles, B is to H as small b is to what? Small h. All right. So we can form a ratio out of this. Okay. So if you are to use what's the name? Tan. If you want to even if you want to use tan, then it's what? Opposites over adjacent. So that is big H over big B will be equal to small b over small h. All right. So that if I want to make small h the subject, then small h is simply b times big B
Divided by
over h. All right.
So,
Yep.
from this, you said, is it not supposed to be big H over big B equal to small h over small b?
It comes down to the same thing. Let me recap it so that we oh sorry. Okay, yeah, sorry. Yeah. All right. That's true. Yeah, sorry. So it's small h over big B. All right, thank you. So h is simply big H over B times B. All right, yeah. So there's it, yeah. Okay, so there's the principle of similar triangles. Okay. So this approach, most of the time, your equation is not 100%. It's fine. Again, we are not looking at accuracy, like exact values per se, right? So here you found you're assuming that the moment at midspan is your highest value, but that is not the case because the moment skews off a little bit towards the right, which is 0.98. Okay. So this is acceptable. All right. This is still acceptable. It's fine. But then the more accurate of the two would be the one that we solved earlier. Okay. The last school of thought that we are done. That should be in only 1 minute. I can decide that instead of drawing my moment due to, the bending moment due to the moment diagrams or the redundant moment, my negative can actually be, I can draw it upwards this way. Okay. This is negative. Then superimpose the positive on it. So I can actually have the positive this way. Okay. Then some just will shade these places. And then that becomes your Benjamin diagram. But I find this a bit interesting. So usually I don't really advise us to do that. All right. So I find that a bit interesting. Yeah, but some books tend to do it sometimes. You find that books going by this approach. Okay. So that if you want to know the maximum moment, let's say in this span, if he has 4, this is what do we get? This is 0.8 over here. So this height here will be the maximum. So you can find the difference between the two. Again, you can find this height here. And again, find this height also somewhere here. All right, so you can do that, but then this is a bit strange sometimes for students. So I usually advise that we just go with one of the two. All right, preferably whether this on the left or on the right is fine. I prefer that one. All right. We're supposed to solve a number of questions. We'll solve more next week, and hopefully that should bring us to the end of the 3-moment equation method. All right. Any questions? So I'll go ahead and stop the recording.